duplicate, but I'll try to complement what Ari presented. I'd like to say that this is a personal view of the state of visualization in medical visualization. And I guess one of the good and bad points of asking two old guys to get up and talk first is that you're going to hear a little bit about the past also, so, but not too much. And then I'd like to talk a little bit about the report that we're reviewing in this panel, see how we've done, what they may have missed, and just a few sentences, a few slides about where we might go. Okay, so I have a history too that's actually quite similar to what Ari talked about. As Ari mentioned, we first developed marching cubes in 1984, and NCSA, the National Center for Supercomputing Applications, was formed in 1986. All right, and this was really, I think, part of this report was motivated by the fact that NCSA had been formed. We're here today to talk about the '87 report and see how we've done. Now, we had the seminal graphics volume rendering paper of Pixar, 1988, and as Ari said, the first workshops. And if you remember, we had graphic supercomputers, Stellar and Ardent. Dave Laidlaw knows that field well. Yeah. And the first conference, and I guess Ari left off the visualization toolkit textbook. It's okay. And then, of course, the fantastic fact that we have NIEEE transactions in our field. But first, let's look back a bit further. If you look at the computer graphics vendor pioneers, you'll see names up there that, except maybe for Evans and Sutherland, you just won't recognize. So in the hardware area, this has been a very tough field and continues to be so. But of course, we are dependent upon technologies in these areas. And this was my first graphic supercomputer, a VAX 11780, and this was my first visualization workstation, the Tektronix storage tube. And of course, who can forget the wonderful vector refresh machines from Evans and Sutherland? Our VizLab with our ADM3A and Alexadata frame buffer. This is the sorts of equipment that we first developed our scientific visualization work on. And using shaded graphics, Synthavision, and the first open source graphics package, actually, Movie BYU from Brigham Young University. This is actually mentioned in the '87 report as the only university-supported software package in visualization. So we go through the types of computers that we used in graphics and visualization at the time. My first real machine was a 360 Model 44 and DOS running on a PDP-11, not Bill Gates DOS, but Dex DOS. We had a Lundy vector refresh system. And then we moved up to storage tubes on Honeywell systems running GCOS. And then when we all thought we died and went to heaven, and DEC came out with this wonderful machine, the VAX. But it still had graphics on the side. They were bags that were attached to the sides of these machines. And then once again, we thought we died and went to heaven with workstations that came along. So we had these machines on our desktop and the wonderful Silicon Graphics machines. So we come to 1987, all right. But first, I'd like a little personal interruption because it was a big year for me too. Actually, in RSNA of '86, GE every year buys the back cover of radiology for the RSNA annual RSNA meeting, and Harvey Klein and I and Carl Crawford from GE Medical Systems were on the back cover. And it's interesting what we claimed in this, or what GE claimed. Such stations would enable both radiologists and surgeons to walk through a proposed procedure using actual patient data. Surgical alternatives could be evaluated and refined prior to surgery, possibly reducing patient time in the operating room. Unfortunately, this isn't even true now, but back then, this is what we saw. And this is SIGGRAPH 87. This is actually after I gave the talk, I think, but at SIGGRAPH 87, which was actually, if you look at the session that Ari and I were in, was called volumetric modeling. All right, this is 1987. All right, I think that's pretty good. And then the other areas I've been involved in, this was a SIGGRAPH hat trick at the time. It was a paper, a panel, and a course. With the panel on toolkits and object-oriented geometric modeling and rendering. And then I had a photographer in the audience that I brought with me. But anyway, so let's get back to the report. It's really interesting to read the report because these folks, they're very bright folks, like I hope will be, and they were very insightful in what they said. They, at the time, predicted a convergence of computer graphics, image processing, and computer vision, and that's starting, all right? I mean, there's been some of that. So the sort of thing, although this is my chart, and I look, they have a similar chart in the report, all right? But this notion of the convergence of these different disciplines, of computer graphics, which is really a synthesis of results, and image processing, and computer vision to extract features and create models, and visualization to manipulate all of these and integrate all of these. I mean, one would still argue whether, I don't think the computer vision community thinks they're part of visualization, all right? But one can argue that certainly our discipline's at the center of all these to bring all of these together in our applications. And there was a focus on tool users and tool makers in the report. They said interactions must be fostered between scientists, engineers, and visualization experts. And there are some instances where this happens. Certainly at NCSA in the early days, there was a lot of this going on. And recently, NIH has had is forming some centers to bring medical practitioners, algorithm developers, and software engineers together. All right, so this is still an area that we need to do more in. In the long-term needs, the report said there will be need for higher dimensional visualization of scalar, vector, and tensor data. And this is actually 1987. This is quite insightful to think about this when you think about the sorts of things we can do today that they couldn't even imagine at the time, but they knew there would be these requirements for this. Dynamic visualization of fields and flows. High bandwidth picture networks. Remember, this is pre-internet. I mean, the internet existed, but it was only used by small groups of scientists using very clumsy interfaces. And massive data set handling. And vectorized and parallel algorithms. These are still very important. These are still long-term needs for our community. For opportunities, and I'm just looking at the medical area, they talked about opportunities in diagnostic medicine and surgical planning, which I'll talk about a little bit, and radiation treatment planning, which I won't talk about. But they talked about integrating results from multiple modalities and integrating structural and functional information at multiple levels. This is 1987. It's unbelievable, really. It'll be amazing if we come up with some of these insights, I think, in these next two workshops. The opportunities in 3D brain visualization. Now, at the time, they talked about serial histological sections. This is not non-destructive to the patient. So, fortunately, MRI came along. Remember, MRI was in its infancy then. I remember in 1984, I had the opportunity, I was tacked on the end of a session where Jack Welch, our CEO, was at the R&D Center, and the whole meeting was about MRI. I mean, should we abandon this technology? We can't, the government won't reimburse for this, all right? We're investing hundreds of millions of dollars in this technology. You know, when are we going to be able to use this, right? Also, 3D image understanding. This is in the 87 report. And mapping of brain interconnections in parallel throughout the brain at the level of fiber tracks. Unbelievable. Diffusion tensor imaging. He also talked about a brain mapping factory this is distributed analysis, distributing computation over large systems, over some sort of a network. On the tools ends, they talked about surface models, and there they said, of course, we're going to have to use supercomputers and workstations. So some things we missed a little bit. 3D volume visualization. These are quotes. The field is very new, will require navigation, Ari, virtual colonoscopy, right, in volume-filled imagery. Volume visualization will play a major role in future research environments. I don't think they knew what volume visualization was, but there was this feeling that we were going to go beyond just these planar representations. So how have we done? All right, so I've got some Google hits in here. It's kind of interesting. I ran these last night. So let's look at surface rendering. So I just typed these in double quotes. So this is Marching Cubes 1984, rendered with the open source package, a movie BYU, which was limited to 8192 triangles. Okay? So I could render 2,000 software, 2,000 triangles per second on a $200,000 VAX. Right? That's about $100 a triangle. Okay? 2003, 500,000 triangles on a $1,000 PC. All right, at 0.2 cents per triangle. So certainly, as Ari said, hardware has played a tremendous role in advancing our field and bringing it to end users. And will continue, I agree. In the surface rendering area, since I got paid by the Polygon, I'll have to show some examples. But this institution here has been a tremendous influence on our field with the visible human and the fact that they gave us this data to work with over the years and continue to work with, actually. A lot of these are surface results from Andre Gutierrez, I think when he was at IBM Research from MRI. This is there's a wonderful facility at UT Austin that I discovered as I was preparing the talk. Digimorph, where they're scanning at very high resolution all kinds of animals. All right, this is great. So this is a hummingbird. All right, and these are all rendered with triangles. And then there's been other. We did some work with Stanford on a virtual frog. Now volume rendering, 69,000. This didn't really, the word volume rendering, it didn't really exist in 87. It did a little bit, but now, almost 70,000 hits on Google. More than Marching Cubes, Ari. It's hard to say, but. And of course, these are the sorts of wonderful visualizations that folks can achieve with the high resolution CT scanners. I mean, in the laboratories, people are working on not 64 slice and 128 slice system, but truly volumetric acquisitions. And these are wonderful volume renderings showing the details in the heart. Some beautiful images, Gordon Kindelman, a lot of folks working in this field over the years, just outstanding images. And as Ari said, mixing, bringing together, integrating the sorts of information that we have, at least in the medical area, mixing surfaces and volumes, it's sort of seamless integration. And commercial products. All right, I'll get to this point later, but here's something that was a very new field in 1987. All right, and now one could argue, all right, that if you can go out and if the vendors provide systems that do this, vendors like GE and Siemens and Vital Images, running on systems without any hardware acceleration, just using really good engineers that have worked for years to take the algorithms that have been developed in the late 80s and early 90s. Hundreds of engineers tweaking, writing inner loops in assembler code, and so on, but bringing a solution to radiologists. It's amazing, I think, the progress of volume rendering in these 17 years, from nothing to product. Multimodality imaging, to be honest, is still not utilized all that much, but we're seeing more and more of it. This is some micro CT and micro PET work that we did a few years ago of a mouse. We'll do a registration and then a fusion. And of course, now there are multimodality scanners. Most of the major vendors now have these combined CT and PET scanners, so you get basically co-registered functional and anatomical information. For applications, I'll go over a few applications. In surgical planning and image-guided surgery, surgical planning drove a lot of the early developments in medical visualization because it's such a challenging field and continues to be. And work that we did with Brigham and Women's and then Brigham and Women's with MIT on merging three-dimensional information with real patients in the operating room, or even building custom machines. This is an open magnet that was developed in our research lab that's still running at Brigham and Women's Hospital in Boston, where the surgeon steps inside the magnet and can, as he or she's operating on the patient, can reacquire MRI to make sure all the tumor's been resected, for instance. And wonderful software packages that allow one to do segmentations, and then actually the slicer program, for instance, can actually be merged with the operation. And image-guided surgery. It's a big field. Several companies in this field that allow you to integrate trackers with radiology with new visual information. And virtual colonoscopy, as Ari said. 34,800 hits. It's amazing. Okay, this is early work that we did in 1994 on virtual colonoscopy, and of course this was surface-based work at the time. And the great work that Ari and his group did at Stony Brook and commercialized in the Viatronics system. It's really outstanding. And Dave Vining, actually the founder of the field from Wake Forest, with just wonderful technology. Karl-Heinz Hirni talked last night about digital atlases, and I think this is an area that is going to just explode. We're just at the beginnings of this. We've done a little bit of work with Brigham and Women's Hospital in this area. And Peter Ratou, who has done hand labeling of the thorax of the visible human when he was at Engineering Animation. And the wonderful work that Dr. Hirni and his group did in Hamburg. It's a shame, actually, that we all could not have seen his talk last night. And other folks taking programs like MayaViz and so on, and integrating real data with sort of medical illustrator type data. And I'm really looking forward to tomorrow's talk. MRI diffuse and tensor imaging. I mean, they talked about visualizing the connections in the brain. And here are a couple of examples from Utah and Brigham and Women's. And I really looked, Dave, on your website. I wanted to get a really good image last night. I couldn't find it. I should have asked you for one. Now, things the group missed, all right? What did they miss? They missed the internet. They talked about networking, but the internet really didn't exist. I spent 6 months in Mark Lavoie's lab in 1995, I think, in the fall of 1995, when the internet actually was just commercialized. I mean, they allowed you to do commercial stuff on it. I mean, we had been on it because we were a research lab, and a lot of research labs in all the universities, but you could do commercial stuff on the internet back in that era. And they missed the PC, really. I mean, let's face it, a lot of what we do, we can do on our laptops. They missed open source software, which I think has had a tremendous impact on the field and will continue to do so. And they missed InfoViz, which we'll hear about next. So what's been the impact of this field on medicine? All right, and I'm not going to be cynical, all right? I'm going to try to be truthful as someone who's been in the field and has also experienced the frustration of working in a research lab for a company that does medical imaging, all right, but can do a lot of things in medical imaging, and they're not necessarily impacted by our field. So on medical research, I think we've had a tremendous impact and continue to have an impact. The techniques, the tools that we develop as tool makers for those tools users, okay, I think there's a lot to do there, and working together we can help them even make more impact. In radiology, I think we've just had some impact. Okay, 3D, you can buy it, all right, but lots of times these workstations just sit there. They'll buy them and they'll just sit there, the 3D workstations. Surgery, a little. A lot of great research, but actually being in the operating room, saving money, making patients better, all right, we're just at the beginnings of this. And you go to a community hospital, and we had no effect at all. All right, so that's sort of from the high end to the low end. Okay, now reality. As Ari said, visualization is just a small part of a medical application. We're not the center of things. Even though the pictures we all draw, we put ourselves at the center. We're just a part of it. We are the pipeline to the user, but you know, it includes boring things like annotation and just displaying images and not doing image analysis, archiving, filming, databases. These are things that we don't even talk to these people, right? User interface. The original report actually talked quite a bit about human-computer interface interaction, and we've kind of, as Ari said, I mean, we're not the only ones in computer science that have dropped the ball in this area. Okay, there are a few tough problems in medical visualization. Integrating technology into the workflow. So a radiologist, all right, who is getting overwhelmed with data, even if you volume render it, is just overwhelmed. These CT machines, 512 squared by 800 or 900 slices in a chest exam, looking for 1 centimeter nodules. Unbelievable. All right, but we have to integrate. We can't slow it down. We have to integrate imaging with other information. The data sets are getting larger and larger. The PCs have this crazy, 2 gigabyte limit in the operating system. And a big area is detection and quantification, as Ari also mentioned. And this is for screening and things like image-guided drug trials. Segmentation and modeling. All right. As you'll see, I think some problems have been solved. This is a problem I can't ever see being completely solved. So this is a really rich area to work in. Okay, so for the next so many years, it's time to move beyond pictures. We've basically been producing pictures. And volume rendering is a commodity. Let's declare victory, all right, and move on. I mean, sure, there's still some work to be done, but this is a tremendous victory for our field, I think, to go from nothing to the fact that every vendor in medical imaging now has high-performance volume rendering, whether it's accelerated by hardware or software. We need more image analysis and biomodeling, what I call computational medicine. So I'll talk a little bit later. I mean, one of the things that I'm very interested in, I know there are other people in this room interested in, is the notion of a digital human, all right, that will move beyond just images, but include all sorts of analyses, integration with, from organ down to genome. And I think I might be on time, and that wraps up my talk. Thanks.